Hey everyone, good morning, good afternoon, and good evening. My name is Vishwadeep, and I welcome you all on PW Gatewala channel. Yesterday, we started basics of process and process management. We learned what is the meaning of process, why we call it as a process, not a program. Then we learned how a particular process actually executes in CPU and what are the different states the process can be when it is running. And today we are going to start a new topic, CPU scheduling, which is our primary topic of discussion of this particular series for now. So what is CPU scheduling, why it is called as CPU scheduling, and of course there are a lot of things in this particular topic. But before that, different algorithms are of course there. Before starting those algorithms, we'll have to understand the small stuffs about the CPU scheduling. So we have discussed yesterday these things. Today we are going to discuss process scheduling, scheduling algorithms, FCFS scheduling, and one more topic, which is type of schedulers. There are different types of schedulers we have. What those types of schedulers are and why those are called as schedulers, we will be discussing in this particular chapter. Okay, so before we start, just comment in the comment box that you guys are ready for today's learning and my audio video both are fine for you guys, so that we can continue today's discussion. Can you please let me know if my audio video are fine? And of course, you must be ready for learning today. If you guys are ready, just let me know in the comment box so that we can start the discussion of the day. Okay, yes, great. So first of all, process scheduling. First of all, you tell me what is the basic word meaning of scheduling. What is the meaning of scheduling? What is the meaning of scheduling? Giving some kind of a time or a slot in your life for something. Let's say you want to schedule your GATE courses, GATE learning. So what you will say? Next 1 month, morning slot, I'll study mathematics, evening slot, I'll study data structures. This is scheduling only, scheduling of courses in your daily routine. Same thing. We will have to schedule the process. Who will schedule the process? Operating system. Why? See, just because we have multiple processes. See, it's very simple. If you have, let's say, GATE subject, only single subject is there in your GATE syllabus. There is no any scheduling required. You take that single subject, study that, pass it and done. Something said scheduling is required? No. Only one task is there, no scheduling is required. But if you have multiple tasks to be done, then among those tasks, at what time you will do what, for that scheduling is required. Same thing happens. We are talking about multi-programming system. Yesterday we discussed it, na? Yesterday I told you, na? Multi-programming system only we are talking. So we have more than one programs or processes in main memory. Among them, which process will run in CPU, which process will use which IO device. For every single thing, operating system will have to decide based on some criteria. But sir, why criteria? One by one, whichever process comes, based on that, you just allot. The thing is, boss, you do scheduling for the better performance, better execution and performance, better utilization of resources. Simple. So the basic need of process scheduling is to improve system performance. If processes will be scheduled in better manner, when a process will run, when a process will do IO operation, etc., in that case, my system's performance and resource utilization can improve. But later on, slowly, when we will go further and we'll see the algorithms, scheduling algorithms and all, we will understand there are more criterias. It's not about that quick execution, early execution of processes. It's not that. There are more other criterias which we will try to achieve. There are more different goals which we will try to achieve by scheduling the processes. Okay. Now, next is scheduling queues. what happens? We have seen different types of states. If you remember this diagram, we have a new state, ready state, waiting or blocked state, running state, terminated state. These states yesterday we have seen. When we have more than one processes in a state, let's say new state, so many processes are there. So operating system makes a collection of all those processes which are in the new state and keep them in a list. That list is called as job queue. Job queue. So job queue is one of the data structure or a list you can understand where all those processes are kept which are in the new state. Okay, understood? So name job queue just because all the jobs which are in the new state kept here. All processes which are in new state are kept in this queue. Job queue. Okay, fine. Next is ready queue. This is important, boss. Why? Just because in this CPU scheduling chapter, this ready queue will be used so many times and at so many places. What is ready queue? Ready queue is that particular queue which is used to store or which is used to keep all those processes which are in ready state. We have seen yesterday lot of processes admitted, they are in the main memory, but all are not running. So some will be in the ready state, waiting for the CPU to run, right? So in that case, what happens? All those processes which are in the ready state are kept into ready queue so that operating system will have a list of all those processes which are in the ready state. So OS will have a view. Okay, these processes are there which are in the ready state. So for that, I am writing the definition here. All processes which are in ready state are kept into this particular queue. When we will go with the CPU scheduling, we will have to have visibility of this ready queue. What are the processes we have in the ready queue? Among them, which process will have to schedule to run on CPU? That is what the task we are going to discuss in the near future. Next is device queue. See, we have lot of devices. We have disk, we have printer, we have camera, many other devices. So you know what happens? Devices are very slow as compared to CPU. Very slow. Let's say one process is there. That process is using the disk right now. And two more processes are there which are also waiting for that device, same disk only. But just because first process is using the disk, two process P2 and P3 will have to wait. So where they will wait? In that device's own queue. So for each device, we have a separate queue, means operating system has a separate queue. So if one particular process is using a device, rest of all who want to use that device will have to wait. And where they will wait? In this particular device queue. Understanding? If you guys are understanding, keep chatting, keep typing so that I'll understand that you guys are listening it. So device queue is what? All processes which are waiting for a specific device are kept into that device's device queue. Now I'll ask a simple question. In system, in operating system, how many job queues are needed? How many job queues are needed? Tell me, how many job queues will be there in the system? Only one. One list OS will maintain all new state processes into that. How many ready queues? Only one. All the processes which are in the ready state will be kept in that single queue, all. But how many device queues are needed in operating system? More than one. For each of the device, we have one device queue. So for disk, we have a separate disk queue. For printer, we have a separate printer queue. For camera, we have a separate camera queue. For microphone, we have a separate microphone queue. So it will be like device queues are more than one. Why? For each device, separate queue will be there. Understanding this point? Understanding this point? Next is type of schedulers. See, I already told you guys yesterday. I'll give you a little more enhanced, visibility on this thing. Operating system is a software. That operating system software is very big. It has lots of small program for each small task. For each task, we have a small program. Something like, let's say you open your computer system and right click on your desktop. When you right click on your desktop, some menu is visible, right? For that, showing to that menu also, there is a small program behind. Yes, true. For each and everything operating system does, small, so many programs are there. And such kind of collection of program, a big umbrella we are having under that, keeping all such programs, single software operating system. Now, when I am talking about these three schedulers are also three programs. Just imagine, these are three programs of operating system. And these three programs will do what? This will do certain specific task. This one also, this one also. What happens in that case? Long-term scheduler, the job scheduler does what? And short-term scheduler does what? Medium-term scheduler does what? I'll tell you. So these are three different programs of operating systems and doing some scheduling task. First one, long-term scheduler or job scheduler. This schedules processes from new to ready state. See, we have lots of processes in new state. Among them, which process will come next to ready state? Admitted. That decision taken by whom? Long-term scheduler, job scheduler. So long-term scheduler will bring processes from new to ready state. Which process will come from new to ready state? Decision taken by long-term scheduler. Okay, understood? That long-term scheduler called as job scheduler also. Now, you might have a question. Sir, why it is called as long-term? I'll come to that point. I'll discuss why it is called as long-term. Let me explain you this short-term scheduler or CPU scheduler. See, as I already told you, when we have multiple things, we need scheduling, proper scheduling. We have lot of processes in new state. Among them, which process will be admitted and coming to the ready state? At what time scheduling is needed? Yes. And that is what this job scheduler does. So among multiple new state processes, which process goes to ready state at what time? Decided by this long-term scheduler. Right? Okay. In CPU scheduler or short-term scheduler, we have lot of ready processes. So many processes are there which are in the ready queue, in the ready state and waiting for CPU. Let's say 4 processes are there, P1, P2, P3, P4. All are ready to run on CPU. Now among those 4, which process should run first? That is decided by CPU scheduler, short-term scheduler. So short-term scheduler does what? Short-term scheduler schedules a process. Which process will run next on CPU? Will take that transition ready to running. Look at this scheduler. So what happens? This short-term scheduler does what? it decides which ready process will run next in CPU. So it just decides that among all the ready state processes, which process will run next in CPU. Great enough. Next is medium term scheduler. But before that, okay, let me just tell you the difference between these two. I'll ask a simple question to you guys. You will have to answer this question. How many times you open a new app? How frequently? How frequently you open a new app? Whenever you want to open a new app means that app was not running before, now you want to open it. Anytime it happens, a new process comes from new to ready state. Okay? Yesterday also I told the same thing. How frequently you do that? Every 5 minutes, one process in a day. Every 10 minutes, every 15 minutes, maybe every 1 minute. Let's say every 1 minute, one process. Fine. Now look at this. The frequency in which that long-term scheduler is required may be in seconds or minutes. The long-term scheduler will schedule one new process that will be taking this transition coming from new to ready state 1 minute per process or one process per minute. But you know what? If a process is decided that that process will go for running in CPU, it will hardly run for a few nanoseconds. How much? Few nanoseconds. And after that, either it will be preempted or it will go for IO operation, and short-term scheduler will need another process to be scheduled. Which means the need of short-term scheduler or that CPU scheduler is very frequently. Every few nanoseconds, short-term scheduler need is needed. Though that's why the name is what? Long term and short term. This scheduler needed less frequently in the long terms needed. This scheduler needed quickly in the quick frequent manner. This scheduler is needed. That's why short term scheduler. In the short terms only the scheduler is needed. That's why these two names. I hope you guys are understanding now what am I saying here. Are you guys understanding what am I saying here? Yeah, one more thing I want to ask. Am I speaking little quickly for you guys? If my speaking is fine, I mean my pace is fine for you guys, tempo of my statements are fine, please let me know. Sometimes it happens that I speak very quickly, long statements. So you'll have to tell me. Okay? Fine? Okay, let's go for the next thing. Medium term scheduler. For explaining this medium term scheduler, I do have a story for you guys. You guys play games in your phone? Have you ever played any game in your phone? Ever? Played? Anytime? Are tell me re baba, have you ever played any game in your phone? If you have, then you will understand this example. So let's assume this is main memory, RAM. We know that whenever we have a running process, current running process, that should be there in your RAM. Now let's assume one fine day you decided that I do have little extra time, so I'll play a game. Game is very heavy, means big in the size. So apart from operating system, you open the app, that game, and that game comes into your RAM. That game is very big, so it takes this much of space in your RAM. You are playing, and suddenly a WhatsApp message comes from one of your friends asking that, did you submit assignment? At first place, you will have a small heart attack, mini heart attack. Assignment? Which assignment? Oh, assignment, that subject. I completely forgot. Now will you what? Will you do what? You will pause the game and you will open the WhatsApp chat of your friend. Hey, I did not submit. When is the last date? Friend is saying today. In next 2 hours, deadline is getting over. And you are like, oh, now what to do? So right now, you know what you did. Apart from game, you have opened another application which is WhatsApp. So WhatsApp also should be there in the RAM. Of course, WhatsApp also comes in your RAM here. Now your friend says, don't worry boss, I have covered you. I have sent you a mail. In that mail, I am having my copy of assignment. Just modify it a bit, write your name in the file, update it and share it. Okay, you'll be saying, you are only my best friend, buddy. I will treat you. Definitely, I'll give you a treat. One ice cream, one chai, one coffee, whatever your friends are liking, one from my end. Okay, so you will open your Gmail now. Why? Just because your friend has sent a mail. So WhatsApp is there in the background. It is open. Game you have paused for some time, and you will open Gmail. In the Gmail, there is a file. That file is in text format. You open that file in text format. As soon as you open that file in the text format, some kind of text reader, let's say Microsoft Word or something, should be there in your phone that opens that particular file. What happens in that case? In that case, my systems understand that main memory is now not having any extra space. But user wants to open Microsoft Word. What system does? Operating system understands that when there is no any enough space in main memory, but there is one program game which user has not used for long. So that game is removed from the main memory. Yes, that is true. It happens. So what happens? To clear this space of main memory, what this operating system will do, this particular game is moved out of the main memory and kept in secondary memory disk, magnetic disk or SSD, whatever you have. Okay, that game software is moved out so that main memory RAM can have extra space. Now if you say open the text editor, fine, it will open. So your text editor or maybe MS Word will be open and your file will be visible to you. In the list of open files, or sorry, in the list of open applications, that what applications are running, game is still visible, only list, but its content is removed. Only list, the forward front page you can see, okay, game is there in the main memory. Something like in my phone, I can see here when I just scroll up, or maybe in the Android phone, one particular button is there. You tap that particular button, all the open applications you can see. Side to side, you slide your screen and you can see all the applications. But you can see the front page, but it is not there. Actually, game is not there in main memory. It is removed. Why? Why? To bring some other program. Why? Just because main memory was not having enough space. But why only game chosen? Just because one of the reason is it was not being used for long. It might possible that WhatsApp application can be removed or some other process can be removed. Yes, but who decides that? Medium term scheduler. So here medium term scheduler is taking one process out of main memory so that main memory can have enough space for other processes which you want to run. This particular thing is called as swapping out or swap out. This process called as swap out. So process is swapped out, main memory. Yes, a new process admitted so that MS Word you can run. Now you will edit that in MS Word, write your name, roll number, etc., some variable name, etc. You changed in that assignment, saved it, fine. You will close the MS Word. Then you will go to Gmail, you will send that Gmail to your professor for submission of that assignment. You are happy, you will close the Gmail also. After that, on WhatsApp you will send message to your friend that okay, my submission is over, and in the group also you'll inform to your friends that if somebody is not submitted, please do that, etc., whatever. Now you will go back to game. What happens? You have removed this, already gone, already gone, already gone. Enough space is there? Yes. Now when you open the game, this is the real world situation. I have also seen same kind of situation. When I'll go back to game, front page is there, but I will see game loading again. Happened many a times, it has happened with me when I used to play games before in my mobile phone. So game will be seen loading. Why? Just because it was swapped out before, now again medium term scheduler, it will swap in. So medium term scheduler again will be swapping in that particular game. Fine? Understood? What am I saying? Are you guys understanding? If you are watching this lecture recorded also, you'll have to write down in the comment box later on that yes, you understood the things. If you have doubts, share those doubts also in the comment box. I'll read and answer. So game, swap out, then later on swap, oh, not out, swap in. Later on it will be swapped in. Who does this swap out, swap in thing? Medium term scheduler. On basis of what? Many criteria there. One process which has not been used for long, swap it out. If a process having lower priority, swap out. Many things are there. But swapping, who is doing swapping? Medium term scheduler. After swapping out a process where it is kept in the disk, there is a special space created for that, and that space is called as swap space. There is a swap space created in the disk where swapped out processes are kept. Okay, so medium term scheduler does what? Performs swapping of processes. Great. I'm sorry, really sorry, my throat is not doing well since last 1 week. Okay, now next we are going to concentrate on this. Lot of ready processes will be having. Among them, we will try to run a particular process. Which process will run in CPU? That decision we will make, and for that we have different algorithms to be discussed. Okay, but now one more point we'll have to discuss over here before this is when a medium term scheduler swaps out a process. Previously, when you pause the game, that game goes to the blocked or waiting state. When you will again try to run it, it will again go to ready and then running state. But if a process is paused right now, game is paused, it is in the blocked state. Now you know what happens when a process is in blocked state or somewhere else and you have swapped it out. When you have swapped it out, then the state of the process will be what? For that, we'll have to understand that when a process is swapped out, the process state is called as suspended. When a process is swapped out, the state is called as suspended. From which state you can swap out a process? Either a process is in blocked state and swap out done, yes, possible. It is in ready state and swapped out, possible, yes. From running, a process cannot be swapped out. And yesterday I told you, if a process is in these three states, then only it is in main memory. New state cannot be swapped out. Why? Array process is not there in main memory at all. Why to swap it out? Terminated, already finished. Why? You will swap out a process which is already terminated. If process is terminated, it will not be in main memory. Swapping not needed at all. So swap out can be done only from these two states. If any process is in the blocked state or waiting state, waiting or blocked, and if it is swapped out, what happens? It goes to suspended blocked state. So when a process is suspended, then it will go to suspended blocked state from blocked. And if its suspension is over, resume, then that particular process comes back to again blocked state. Means if process is swapped out from the blocked state, previously it was in blocked state, swap out of the main memory, it goes to suspended blocked state. If again brought to main memory, here swap in, then called as again blocked state. Next, ready state. If a process is in ready state and it is blocked, it is suspended, then what happens? That process will go to suspended ready state. When process come back, resume, it will come back to ready state. But sometimes it happens that a process was in blocked state, its IO is working, but still it is swapped out. When processes IO was working, happening, but still it is moved out of the main memory, suspended block. When its IO operation is done, still it is suspended. Process is suspended, but IO operation is done. If IO operation is done, process cannot be in blocked state. It should move to the ready state. But it is suspended, yes, so it will go to suspended ready. When IO or event is completed, but still process is suspended, then it will move to suspended ready state. Okay, I do have an example for this. Very simple. You guys follow some sport? Any sports, let's say cricket. My favorite sport it is. Let's say you follow a cricket. There is a cricketer. That particular cricketer got injured. And because of injury, that fellow will be out of the games for next 2 months. The cricketer will take 2 months to recover from injury. 2 months. So that fellow is right now in blocked state. 2 months out of the game because of injury. Now, during his or her injury period or recovery period, he has done some kind of illegal activity. Let's say taken some kind of illegal substances or done some kind of, disciplinary uh, act. Because of that, the cricketing body in India, we have cricketing body called as BCCI. BCCI has suspended that fellow for 3 months. 3 months. So 2 months anyway injured, but got suspended for 3 months. So already in injury break and also suspended also for 3 months. Now what happens? Look at this. Suspended was there in the blocked. From blocked to suspended. You know what happens? After 2 months, the cricketer's injury over. But still, cricketer cannot be chosen for the games. Why? Just because that fellow is suspended. But his injury period is over now. Blocking waiting is over. Yes. So what happens? That fellow was suspended also, blocked also. Now blocking is done. Why? Just because IO operation over, injury period over, recovery over. So that fellow will go to suspended ready state. So that fellow will be in the suspension only, suspended only, but ready. As soon as suspension is over, that fellow will be ready to be chosen for next tour, next tournament. Understood that point? So if any process is suspended from blocked state, but its IO operation is done. So that process will be suspended only, but now suspended ready state. This is your updated process state transition diagram, but still point is still true that yesterday I told in these three states when a process is, then only process in main memory. Terminated, not in main memory. New, not in main memory. I'm sorry. If process is in these two states also, not in main memory. Why? Array, we are removing a process in from main memory, then only it will be suspended. Na? Swapped out, then only suspended. Yes. We are bringing it to the disk. That's why. Fine. Okay. Now CPU scheduling. We are talking about process scheduling. Yes. Process scheduling is done from multiple place to multiple places. Process scheduling is done by long-term scheduler when a process comes from new to ready state. Process scheduling is done here in blocked state also when multiple processes are waiting for a device, which process should use the device. And process scheduling is done when which particular process should go to run from ready state. That is the CPU scheduling. So CPU scheduling means here this one. Which process should run on CPU next among all the ready processes, that is CPU schedule. So that particular CPU scheduling's function is what? What is its work? Make a selection. Which process runs next in CPU among all ready state processes. Okay. What is the goal? Minimizing the waiting time, turnaround time, maximizing the utilization of CPU. Okay, this is another point. And fairness. Next point it is. And another point is there. Maximizing interactivity. See, the thing is, different scheduling algorithms will bring different advantages. Some algorithms will bring fairness, no biased result. All the processes will be treated as fair equally. Some processes will bring interactivities, or some algorithms will bring interactivity. Some algorithms will try to minimize the wait time and turnaround time. What is that? I'll explain in some while. And some algorithms will try to maximize the utilization of CPU. Means throughput. They'll try to increase the throughput. Now, which algorithm does what, how, before that, we'll have to understand this CPU scheduling types. So two types of schedulings are there, which are nothing but the type of multi-programming also. One is non-preemptive, one is preemptive. And you guys already know that now. Non-preemptive means once a process is scheduled to run on CPU, it will complete, then only it will leave the CPU. Forcefully preemption not possible. Preemption means taking out a process from CPU even if process is not completed. Even if process does not want. At that time also, if you can take out the process from CPU, that is called as preemptive. So preemptive scheduling algorithms will allow preemption because of certain criteria. If there is a running process, that process will be taken out of the CPU and other process will be given to the CPU. Some criteria based on algorithm. We'll learn that. So you understood already yesterday only we have discussed non-preemptive and preemptive. Non-preemptive means a process given to CPU, it will run until it wants. Preemptive process can be taken out of the CPU forcefully. Okay, now These are the times which we'll have to understand. First one is, these are the times which will be attached with each process. Each process, yes. For each process, we'll have its arrival time, its service time, completion time, turnaround time, waiting time, response time, everything. For each process, what are these? Arrival time. What is arrival time? Anybody knows? Time at which a new process arrives. So whenever a process arrives in the system, arrives means in the ready state. Look at this. Whenever a new process is admitted, at what time it comes first in the ready state, that is called as its arrival time. Okay, that will be a time instance, that at what time exactly the process has arrived. That is its arrival time. Now next is burst time or service time. This is amount of time. Amount of time means, see, this is the time in the clock. This is the time of amount, 1 hour, 2 hour, 15 seconds, 13 seconds, like this. This is 1 o'clock, 2 o'clock, 2:15, 2:16, like this. It is the time instance. This is the amount of time. How much total time needed for the process to run on CPU, burst time or service time. So I'm writing amount of time needed by a process to run on CPU. That is what? Service time or burst time. Next is completion time. This is again a time instance. At what time process completed? Completed means terminated. Process was running, and when it is completed, terminated at what time? 2 o'clock, 3 o'clock, 3:15, 3:16, 3:18. At what time process completed? That is the completion time. So it is again a specific time in the clock at which process completes execution. Sorry. Really sorry. Next is turnaround time. Turnaround time says what? It says a particular process spends how much time in the system when it arrives, from there to when it completes. Arrival to complete, how much time a process spends in the system, turnaround time. Writing it. So turnaround time is time spent by a process from arrival to completion. Okay. If I ask a simple question, a process arrives at 10:15 and completes at 10:18. How much time process has spent in the system? 3 minutes. 10:15 to 10:18, 3 minutes total time spent by the process, called as turnaround time. In that 3-minute process did what? We'll see later on what a process can do in those 3 minutes. Of course, it will run for some time in CPU. Sometimes it may wait for CPU in the ready state. So 3 minute, how did you calculate? Completion time minus arrival time. So I'll write down here the formula. Turn around time, which we will denote as TAT in short, is completion time minus arrival time. Like this. Next is waiting time. Of course, whenever a process comes and arrives, process will always not running. So many processes are there. Among those, one process if running, remaining processes will have to wait in the ready state. So how much time a specific process waits in the ready state, that is called as its waiting time. So waiting time is what? The amount of time a process spends or process waits in ready state. That is its waiting time. Just because process was waiting, when my chance will come, I'll run. That is total waiting time of the process. Now see, if I say a process arrives at 10:15, completes at 10:18, and it was running on CPU for 2 minutes. 3 minutes total turnaround time, process spent total time 3 minutes in the system. Among those 3 minutes, process was running only 2 minutes on the CPU. What process was doing for 1 minute? Process was waiting for 1 minute in the ready state. Just because other process was running in CPU, hence this process had to wait. So if I want to calculate waiting time, it will be from turnaround time, total time spent in the system, you subtract the total running time of process on CPU burst time. So if among 3 minutes completion time, 2 minute a process was running on CPU, 1 minute waiting. So if I will have to calculate waiting time of a process, that will be turnaround time minus burst time of a process. That's how you can calculate. Next is response time. Response time is what? When a process arrives, from there, at what time process gets its first chance to run on CPU. When it runs, it gives some kind of response to the user. Whenever process arrives, after that, how much time process takes so that it can run for the first time in CPU and can give some kind of response to the user. Okay, I'm running. Look at this. This is my response to you. So response time is nothing but time from arrival of a process to or till first response of CPU of a process. How does it or how it will be calculated? We'll see that in the questions. Okay. So now these are the two formulas you'll have to remember for solving the question. Let's go to the scheduling algorithms. Different algorithms we have. A lot of algorithms we have. FCFS, SJF, SRTF, priority based, round robin, multi-level, queue scheduling, multi-level feedback queue scheduling, and so on. Okay, now full form. First come first serve, shortest job first, shortest remaining time first. These are the full forms only. One by one, we will see that. Okay, let's see. First come, first serve. In the first come, first serve, on what basis we will schedule a process to run on the CPU? The criteria is arrival time. Whichever process arrives first, of course, its arrival time will be smaller. That process will be scheduled first. First come, first serve. Whoever comes first, arrives first, should be scheduled first. So in their arrival time order, the processes will be scheduled. But sir, if two processes will have the same arrival time, then there should be a tiebreaker. Yes. So in that case, the tiebreaker will be the smaller process ID first. What does it mean? If two processes are there, let's say P1 and P2, and their arrival time given in the system 00. Both processes running on arriving at same time 00. Now which process arrives first? Sir, both are arriving at the same time. So arrival time same to same, tie. Okay, in FCFS we will use the smaller ID. Process ID will be different, definitely. Process ID will be different only. सर हिंदी में नहीं होगा बेटा, इंग्लिश चैनल पे हिंदी में कैसे पढ़ाएंगे हम? दिस इज द इंग्लिश चैनल ना. When you will have the lectures on our हिंदी चैनल, हिंदी चैनल है ना हमारा, जो हमारा ब्रांच का चैनल है, गेट वाला, CSECE वाला, ऑन दैट चैनल आई विल ब्रिंग इट हिंदी ऑल्सो. अभी तो इंग्लिश में, जस्ट बिकॉज इट्स इन इंग्लिश चैनल. ठीक है, वहां पे अलग से हिंदी में पढ़ाएंगे. Okay, so criteria is smaller arrival time first, but if processes are having equal arrival time, then process ID. Always you will have different processes with different ID. ID to, do you have roll number same to same with other friends? No, na. Your roll number and other friends' roll number is different. University roll number all are different, na. Yes, unique for sure. So process IDs also will be unique. Type of algorithm. The type of this algorithm is non-preemptive. A process, if given to run on CPU, will completely run. Okay, let's solve a question. So such kind of process scenarios will be given to you guys. Multiple processes and their ID, their arrival times and their burst times. How much time a process runs. Right now, see, in this example, we have that option also, that process when ready, go for running. It may go for termination, it may go for IO. But this particular case we are not considering right now, just because most of the 99% questions will not have any IO requirement for the processes in this topic. So there is no any IO requirement. Process will run, terminate. That's it. This transition right now is not there for us. Okay, great. We are happy with that, sir. So process having arrival and burst time on CPU, once their burst time of CPU over, process completed. So P1 process arrival 0, burst time total 24 time needed. P2 arrives at 0, total 3 time needed on the CPU. P3 process arrives at 0, burst time 3. Okay, now to understand the scheduling, we'll have to make a chart. That particular chart is called as Gantt chart, Gantt. And this Gantt chart is nothing but the timeline diagram. From what time to what time you will run which process. It is exactly same timetable which you make for yourself. Ideally, you make for yourself. I'm not saying you follow. I'm just saying make for yourself. How much you follow it, you only know. Every time you make a timetable, doesn't work at all. But let's say you might have worked on this particular thing, na? Say at morning 6 o'clock I'll get up, so 6 to 6:30 morning activities, brush, etc., etc. Then 6:30 to 8:30 I'll study mathematics. Then 8:30 to 9:30 my breakfast break. Then 9:30 to this. This is not time diagram. Same thing you will be having here also. Same to same. At what time to what time you will run which process, that is what the timeline diagram. So Gantt chart always starts from 0. Okay, remember, always starts from 0. At time 0, my scheduler will search, CPU scheduler will search how many processes are there in the ready state. So we'll check out here in this scenario, time 0, how many processes arrived already. Sir, all 3 arrived. So in the ready queue, in the ready state, ready queue is there. In the ready queue, all 3 processes, P1 is also there, P2 is also there, P3 is also there. My scheduler's task is to choose one process among them. Which process will run in CPU? FCFS algorithm is implemented. It says the process with minimum arrival time. Hey, minimum, it is equal. All processes are having equal burst, equal arrival time. So if processes are having equal arrival time, tiebreaker is what? Tiebreaker is smaller process ID first. So among them, if all processes arrive at same time, tiebreaker says process ID first. P1 is having minimum ID, so I will schedule P1 at time 0. Scheduled? Yes. The process algorithm This one is non-preemptive. Means if P1 is given to the CPU, then P1 will run completely. I remember one of the dialogue in Hindi from one of the movie, एक बार जो मैंने कमिटमेंट कर दी तो फिर मैं अपने आप की भी नहीं सुनता. OS says if I have done a commitment to run P1, then P1 will complete now. So P1 will take how much time? 24. From 0 to 24 time unit, P1 will run. After 24 time unit, what happens? P1 completed. In the ready queue now, two processes are remaining, P2 and P3. Among P2 and P3, which process is running next? Arrival time is my criteria, but both are having arrival time 00 only. So ID. P2 is having smaller ID, P2 will run. From 24, P2 will take how much time? 3. After 24, 25, 26, 27. So 24 plus 3 up to 27 time unit, P2 will run. P2 also gone, completed, yes. Only one process P3 remaining. Only one process P3 remaining. P3 will run next. No choice, no option at all. So P3 runs, how much time it takes in the CPU? 3. After 27, it runs till 30. Can you please confirm if you guys understood what is the Gantt chart? How does it create, how we created it? Quickly, quickly, quickly. How did we create that Gantt chart? Did you understand? If yes, then we'll go next. Okay. So based on this Gantt chart, once this Gantt chart is over, based on that, we will make certain different calculations. What are those? Completion time, turnaround time, and waiting time. Okay, let's go, let's go, let's go. How? Look at this. See our completion time we will see from here. Can you please check out this diagram and can you tell me at what time P1 is completing? At what time P1 is completing? Sir, at 24 time unit P1 completed, fully completed, finish, done. So what is the completion time of P1? 24. I'll write it down here, 24. P2, at what time in this timeline diagram P2 completes? At 27. At what time P3 completes? 30. P3 starting at 27, finishing at 30. Done. Okay, next we will calculate turnaround time. Completion time minus arrival time. Okay, completion time minus arrival time. P1's completion time 24, arrival time 0. 24 minus 0, 24. So P1 is spending total 24 time unit in the system. Look at this. It arrives at 0, completes at 24, 24 time unit P1 spent in the system. P2, 27 minus 0. So total 27 time unit P2 spends in the system. 30 minus 0 for P3. Total 30 time unit P3 spends in the system. Waiting time, what is waiting time? Turnaround time minus burst time. Turnaround time minus burst time, let's do that. P1 turnaround time 24, burst time 24, waiting 0. P1 does not wait. Waiting time 0. P2 27 minus 3. P2 waits for 24 time unit. P3 30 minus 3. 27 time unit. So these are different turnaround times and waiting times of each process. Now from these, you might be asked a question about average turnaround time and average waiting time. Can you calculate how much average turnaround time we have for all processes? How to calculate average? All turnaround time summation divided by 3. Why 3? 3 processes are there. That's why 3. Per process, what is the average turnaround time? 24 plus 27 plus 30 divided by 3 is 27. Okay. And what is average waiting time of the processes here? On an average, how much waiting time is there? 0 plus 24 plus 27 divided by 3. Average of these three values. 2 2 4 4 11 51 17 51 17. Just check it out. Just check it out if average calculations are complete, clearly understandable for you guys. And how to do that, you understood. Okay, now what type of questions they may ask? First type of question. Of course, such kind of scenario will be given. First type of question they will ask is, in what sequence processes will run? First of all, P1, then P2, then P3, or P1, then P3, then P2, or P2, then P3, then P1, or what? Sequence they will ask. In what sequence processes are completing? I can tell from this particular Gantt chart. Second type of question is, they may ask completion time of a specific one process. What is the completion time of P2? Batao. NAT type question, numerical answer. So completion time of P2 is 27. Any one value among these they may ask. Or turnaround time of a process P3, or turnaround time of a process P1, something like this. Or waiting time of specific process. What is the waiting time of P1? Or what is the waiting time of P4, P3, like this. Or average turnaround time or average waiting time. Among them, any one thing they may ask, and everything is there in this particular page. And that is very easy once you draw this Gantt chart. Once you draw this Gantt chart, everything is easy. Okay, let's do one thing. We have a question. That question you take as a homework, practice, and tomorrow when we will meet, I mean next Monday, next class will be on Monday. When we will meet, we will solve this question and we'll go ahead with the analysis of FCFS, some other type of conceptual questions, and then we will take another algorithm called as SJF, shortest job first. Cool. So all the members who are listening this particular video recorded also, I will certainly expect from you guys that please solve this question. It's very easy. For practice, it's very easy, but we'll have certain more learning out of that. Okay. Thank you so much for listening this particular video. If any doubt still remaining, please drop in the comment box so that we can take it up and solve your queries. Thank you once again. Happy learning. Bye-bye.